Thank you for the introduction. And my name is Yifan, and I'm from Georgia Tech. And this is a joint work with my advisor, Sahil, who is over there. Okay, so let's start from a very simple setting. And there is one single seller who wants to sell one single item to one buyer. And the buyer has a value V, which is drawn from a distribution D. And we further assume in this talk that the values are bounded between 0 and 1. And the strategy for the seller is quite simple. She just wants to post a price P, and the item gets sold if the value V is greater than P. Otherwise, the item remains unsold. And the goal of the seller is to maximize the revenue. So basically, she wants to maximize to find the price P star that maximizes the function of R of P, where R of P is defined to be P times 1 minus F of P, where P is the price and the term F1 minus F of P simply refers to the probability that the item is sold. And this is actually the optimal option that achieves the best revenue, and this result is given by the well-known Myers lemma. And if the distribution itself is known to the seller, then the seller can simply calculate this RP function and find the optimal price P star. But in many real-world scenarios, usually the buyer's valuation distribution is unknown. And the seller can only try to learn this valuation distribution by playing some kind of repeated auctions. And this inspires us to present the following bandit posted pricing model. In this model, basically the learner or the seller is exactly trying to learn the value of P star by playing repeated auction for T days. In each day, the seller posts a price and the buyer draws a value V from the distribution, and the item gets sold if V is greater than P, otherwise it's not sold. And the seller is going to observe whether the item is sold as the feedback in each day. And basically, this is also a bandit feedback, because if the item is sold, the seller can observe a reward, which is exactly P. And if the reward is 0, it means that the item is not sold. And the goal of the seller is to minimize the regret, which is defined to be the difference between the optimal revenue achieved by the optimal price minus the total revenue from these T-day auctions. And this is actually a very well-known model, and it was originally proposed by Bobby Kleinberg and Tom Layton in 2003. In that paper, they showed that for this kind of a problem, there is a T to the 2/3 regret upper bound. And this upper bound is tied up to log factors, and the corresponding lower bound, T to the 2/3 lower bound, is given by a SODA 23 paper from Lamy, Sivantan, and Wara. So it seems that the main part of this problem is kind of already solved. So in this talk, we will be focusing on some specific details of this kind of bandit positive pricing problem. Basically, we want to ask that, can we achieve a better regret bound, assuming that we have some special classes of distributions? Or to be more specific, we want to ask the following question, that can we do better, achieve a better regret bound specifically for the regular buyer? And our main result is to show that this is possible. We give a square root T regret algorithm for the bandit positive pricing problem, assuming the buyer has a regular valuation distribution. And this square root T upper bound also matched the square root T lower bound provided in the same SODA paper from Lamy, Sivantan, and Wara. And our second result is to further extend this kind of a bandit posted pricing model to a more general bandit sequential posted pricing model. And basically what we do is that we extend the square root T result for single buyer to a poly n times square root T regret bound for the general n sequential buyer setting. And we also observe that the same techniques we are generalizing the single buyer setting to sequential buyer setting can work for the more general function class, distribution class as well. And we give a corresponding poly n times T to the 2/3 regret bound for general buyers. So these are our two main results. And in this talk, I will be mainly focusing on the first square root T regret algorithm. And at the end of the talk, I will briefly discuss the bandit sequential positive problem as well. Yes.
General buyer means just having n buyers, or something else?
So for the sequential positive buyer, just means that n buyers are arriving sequentially, each has a distribution, and we can post n prices for different buyers. And we will talk more about this in details at the end of the talk. So for the audience that does not know irregular distributions very well, let me first give you a very brief introduction. A distribution D with a CDF capital F and PDF small f is called to be regular when the virtual valuation function phi v, which is defined to be v minus 1 minus capital F over small f, is non-decreasing. So this class of regular distributions is already including many classic distributions like uniform, Gaussian, and exponential distribution. Well, the class of regular distribution is quite important, especially in the auction theory, because if we have all buyers to be regular, then the standard Myers mechanism will be simplified to be a second price auction on those virtual value phi v's. And there are also many prior works talking about how to learn a distribution via some access to the samples. And basically, there are two major lines of research. The first line focuses on how we could learn a regular distribution very well via some samples. And one work along this line of research to be pointed out is the paper from Guo, Huang, and Zhang in stock 2019, where they settled down the sample complexity for the Myers mechanism, and they also provided a tight sample complexity specifically for regular buyers as well. And the second line of the research is about learning a regular distribution from threshold queries. So basically, you post a threshold, and you can only see whether the current sample is above or below the threshold. And the two papers talking about this part is from Lehman, Sivan, Teng, and Wora from SODA 23 and EC'23. So basically, our work is more close to the second line of research because the feedback we get is whether the item is sold or not sold in one day. Okay, so now let's go to the main idea of our square root T algorithm. So our main intuition starts from an alternate definition for the regular distribution. So besides the monotonicity of the virtual valuation phi v, there is another definition for the regular distribution. So we can call a distribution to be regular when its revenue curve is concave in the quantile space. Or equivalent, we say that the function of RQ is concave. So here inside the definition of RQ, the Q is representing the probability that the one item is sold, while the inverse function of F star is basically pointing to the corresponding price we are setting. So we now have a very nice concavity inside the quantile space, but this is actually what we really want to do because we are more hoping to have a concavity inside the pricing space. The main reason is that in our kind of bandit positive pricing model, in each round we are posting a price instead of a probability. So what we really need is some kind of concavity in the pricing space. So if instead we have some concavity for the function of RP, then we're almost done because we can just simply apply some kind of standard convex optimization ideas to get some square root T bar. So a natural question to ask is that, does the regularity itself already imply some kind of concavity in the pricing space? And we answer this question to be yes, that we show that the revenue curve of a regular distribution is half concave in the pricing space. So to give you an intuition, I draw a picture of a possible revenue curve for a regular function. And firstly, this function must be single peaked, which means that it must first go up and then go down. And secondly, our half concavity says that this pricing curve must be concave before the optimal price P star. So the left-hand side is concave, while the right-hand side we don't really have. So basically, this is the case. And actually, the proof of this half concavity is quite simple. So I will present a full proof for this. And here is the picture for you to give you intuition. So to give the proof, we first introduce the two ingredients that we want. The first one is the derivative of function phi should be greater than 0 because the phi v is non-decreasing. While the second ingredient is that the derivative of function r should be greater than 0 because we only focus on the left-hand side of optimal price P star, and in that region, the revenue curve is increasing. And what we want to show is that for this region, the function is concave. Or equivalently, we want to show that the second derivative of the revenue function is bounded by 0. And we can achieve we can prove this by simply do a case discussion. The first case is that the value of f prime p is already greater than 0. If this is the case, then immediately we have that r double prime p is bounded by 0 because the two terms inside the definition are both upper bounded by 0. The second case requires some calculations. It's the case that the value of f prime p is lower than 0. And in this case, we just need to write down the definition of r double prime p and then apply the first ingredient we have to replace the term 2 times f squared of p by f prime p times 1 minus capital F of p. And then we use the second inequality together with the assumption that f prime p is bounded by 0 to show that the last expression is bounded by 0. So this is actually the proof.
Is it obvious that r prime p greater than 0 to the left of p star, that it's increasing for regular distributions?
So are you talking about that the revenue curve should be single peaked? So this is true because the concavity in the quantum space, because the quantum space is concave, which means that the quantum space is single peaked. So we can convert it back to the pricing space and to show that the pricing space is also single peaked. Okay. So this gives the proof of the half concavity. So what we have is that we now have a very nice structure, which shows that the revenue curve of the regular distribution should look like this. And next, I will briefly talk about how we can use this half concavity to give the squarity algorithm. I will not give you the details about the algorithm, but I will specifically tell you how we are using the half concavity inside the algorithm. So our goal is the following: that we, given this kind of pricing curve, and we further assume that we already know that P star falls in some interval from L to R. So basically, we are maintaining a confidence interval for the value of P star. And our goal is to further shrink the length of this confidence interval after doing some tests. And the test we are actually doing is the following: that we first take value A and B that trisects the interval L and R, which means that R minus B equals to B minus A equals to A minus L. Then the next step we do is to test price P equals to A and B equals to B for roughly 1 over epsilon square round. And here you can imagine epsilon to be approximately 1 over square root T. So that if we are losing O of epsilon somewhere inside the algorithm, we are fine. So after doing 1 over epsilon square rounds for both prices, we can have some estimate R hat A and R hat B, such that the value of RA and RB should be falling inside the confidence interval with roughly a length of 2 epsilon. So yes, sure. So we now have some confidence intervals. And the first case is that if I in the case that 2 confidence intervals are disjoint, so basically I'm using the case that interval A is below interval B as an example. If we are in this case, and also the case that interval B is below interval A should be symmetric. So I use this as example for both cases. So if we are in the case that 2 intervals are disjoint, then we note that we already know that in this case, the value of RA should be lower than the value of RB. And recall that the revenue curve itself is single peaked. This is sufficient for us to learn that P star should be at least greater than A. So we can update the value of L to A. So this is the first case. The second case is that the value of R hat A and R hat B are roughly similar, which means that the 2 confidence intervals overlap. So in this case, we need to use the property of half concavity, which says the following: that if we have P star that falls between B to R, then the concavity gives us R of P star minus R of B is upper bounded by R of B minus R of A, while R of B minus R of A is roughly 4 times epsilon, which means that R of P star minus R of B is already very small. So we can just simply use R of B as a candidate to represent R of B prime, which means that in the following, we don't really need to test the region from B to R. So we can simply update R to B, which means that after performing this test, we can shrink the length of interval LR by 1/3. So we can just continue run this algorithm until the length of the confidence interval is sufficiently small for us to determine the value of P star. And by applying this idea, we can give a square-root algorithm. Okay, so let's go to the last part of my talk. I will briefly talk about how we generalize the single bias setting to the sequential bias. So in this kind of new sequential positive pricing, the setting is basically trying to extend the single bias thing to n sequential buyers. So we now have n buyers arriving sequentially. So each buyer has some value vi independently drawn from some distribution di, and we can post a single price for each buyer. And our goal is to find a group of good prices to maximize the revenue. And for the bandit version of this problem, basically we will assume that we don't know those value distributions, and we want to learn the optimal prices by playing some repeated auctions for t days. And each day we can play a group of prices, and the buyers can draw a group of values. The first buyer with value vi greater than pi will take the item, and we are going to observe the value of pi or to be our feedback. So this is the model. For this model, the results we get are basically n to the 2.4 times square root t regret when the valuation distributions are all regular. While for the general setting, we have something like n to the 5/3 times a t to the 2/3 regret bound. And so what I want to point out here is that both bounds are tied on t. Okay, so for the last minute, let me briefly talk about the challenge we are facing when generalizing a single buyer to sequential buyers. So the major difference comes from the following. That's for the sequential buyer. If we look at the revenue function for buyer I, it should be looking like P times 1 minus Fi of P plus an extra C times Fi of P term. Well, this extra term represents the expected revenue we are getting if we skip buyer I and go to the suffix buyers. So this really hurts us because the new function I of P is still concave between C and Pi star, but it is not concave between 0 and C. And the main idea we're using to resolve this issue is that we are trying to learn the value of C. So if we can learn the value of C accurately, then we are good. And what we also show is that in the case that we cannot learn the value of C accurately, we have some extra concavity style properties to use inside the interval 0 to C. So we can still apply some similar algorithms to give the same square root t bound. Okay, so let me quickly wrap up my talk for today. So basically in this talk, I present this bandit learning for positive pricing and sequential positive pricing. And the main idea inside my talk is to use the half-concavity for the regular distributions. And our algorithm is basically an interval shrinking algorithm. By doing this interval shrinking recursively, we can get a very good value to P star. And there are some of the open problems listed here, and I'm very happy to discuss those open problems offline. And this is my talk for today. Thank you.